You know, it's pretty easy to think of our skeleton as just a static, lifeless scaffold holding us up. But the truth is, bone is an incredibly dynamic, living tissue. It's constantly growing, repairing itself, and responding to everything we do. So today, we're going to go under the microscope and really understand this amazing process.
So how does this living blueprint actually work? Well, first we'll look at how our bones pull off the incredible feat of growing, not just getting longer, but also stronger. Then we'll dive into the elegant process they use to heal themselves after a break. And finally, we're going to uncover the surprising but vital connection between our solid skeleton and the river of life that flows through us, our blood.
Okay, so to kick things off, we need to understand the master plan. What are the fundamental factors, and who are the key cellular workers responsible for actually building and maintaining our bones?
Right, so bone growth isn't random at all. It's this perfectly orchestrated dance between a whole bunch of factors. Our genetics, they set the foundation. But our diet, hormones, and even the physical stress from exercise are constantly sending signals that shape how our bones develop and stay strong throughout our lives.
To really get how this works, you've got to meet the cellular construction crew. It all starts with osteogenic cells. Think of them as the stem cells that create the builders. The builders themselves, those are the osteoblasts, and they lay down new bone. On the flip side, you've got the osteoclasts, the demolition crew that clears away old bone. And kind of overseeing the whole operation are the osteocytes. They're like the project managers trapped inside the bone matrix, sensing stress and directing the whole show.
So, how in the world does a bone manage to grow in two different directions at the very same time? It's not magic. It uses two totally separate mechanisms. One process makes the bone longer, and a completely different one makes it wider and stronger.
And here we see that incredible balance in action. As those osteoblasts are adding new layers to the outside of the bone, the osteoclasts are busy on the inside, widening the marrow cavity. This lets the bone get thicker and stronger without becoming this solid, super heavy rod. It's a true marvel of biological engineering. Now that we've seen how bones get wider, let's zoom way in, deep inside to the engine of longitudinal growth. This is the place where we actually get taller. This is the epiphyseal plate, but you probably know it as the growth plate. This right here is command central for height. It's a highly organized, multi-layered structure made of cartilage. We're going to take a quick tour through its 5 different zones, starting from the quiet reserve zone up at the top, all the way down to where new bone is actively being formed. We start at the very top in what's called the reserve zone. You can basically think of this as the waiting room. The cartilage cells here, the chondrocytes, are pretty small and inactive. Their main gig is to anchor the growth plate to the end of the bone and act as a reservoir, providing a source of fresh cells for the next, much more active zone. Okay, now things start to get busy. In the proliferative zone, those chondrocytes wake up and just start dividing like crazy. They arrange themselves into these really neat columns, kind of like stacks of coins. And it's this active multiplication and stacking that physically pushes the end of the bone up, which is what actually makes the bone longer.
Once they stop dividing, the cells move into the zone of maturation and hypertrophy. Now, hypertrophy is the key word. It just means they swell up, becoming much, much larger. And this expansion pushes the ends of the bone even further apart, adding yet another boost to the bone's length.
But this growth can't just be cartilage forever, right? So in this next zone, the matrix around these enlarged cells starts to harden with calcium. This calcification actually cuts off their nutrient supply, causing the chondrocytes to die. But they leave behind this hardened cartilage scaffold, which is the perfect foundation for the final step. And here is the absolute key takeaway for how this all works. Remember this, the new bone is always laid down on the shaft side, the diaphysis side of the plate. So as the cartilage grows on one side, bone replaces it from the other. It's effectively chasing the cartilage and elongating the entire bone shaft. But growing isn't the whole story. Not even close. Even after we're fully grown, bone is constantly remodeling itself to adapt to stress and, maybe most remarkably, to orchestrate this complex, beautiful healing process after a fracture. Healing a broken bone isn't a single event. It's more like a highly organized, 4-act play that unfolds over weeks, months, and sometimes even years. It starts immediately with damage control and ends with the bone being almost as strong as it was before the break. So in stage 1, ruptured blood vessels create what's called a hematoma. It's basically a blood clot that stops the bleeding and provides an initial framework. Then over days and weeks, new blood vessels grow into the site and specialized cells create a soft callus. This is made of a tough, flexible material called fibrocartilage, and it acts like a natural splint, bridging the gap between the broken ends.
Next up, that soft callus is gradually replaced by hard, woven bone in a process we call ossification. This creates a bony callus. Now, this woven bone is like a quick, kind of disorganized patch job. So finally, over many months, our demolition crew, the osteoclasts, and our builders, the osteoblasts, get to work remodeling this patch, replacing it with strong, organized, compact bone and restoring the bone's original shape and strength. All right, now for a fascinating shift in gears. We're moving from solid bone to a liquid, but it's a liquid that is technically also a specialized form of connective tissue, blood. Now, how can a liquid be a connective tissue? Let's find out.
If you were to take a vial of blood and spin it in a centrifuge, it would separate out into two main parts. About 55% of it is this yellowish liquid called plasma, and the other 45% is made up of the heavier stuff, the cellular components, like red and white blood cells.
And this is exactly why blood is considered a connective tissue. Just like our solid tissues hold our body together structurally, blood connects our body systems on a functional level. Its cells are just suspended in a liquid matrix, the plasma, and it's constantly transporting nutrients, oxygen, hormones, and waste, linking every single part of the body.
So let's take a closer look at the different types of cells floating around in this river of life, and the plasma that they call home. And this brings us full circle, right back to the bone itself. I mean, where do all these different blood cells even come from? Well, they all originate from a single type of stem cell, the hematopoietic stem cell, and it's located deep inside our bone marrow. The factory for our blood is literally inside our bones. The connection between these two tissues is just undeniable.
Now, the plasma itself is mostly water, but it's the proteins dissolved inside it that are doing all the critical jobs. You've got albumin, which helps maintain blood volume and transports molecules. Globulins include the antibodies that fight off infection, and fibrinogen is absolutely essential for forming blood clots.
So we end with this question. How might a disorder affecting the bone marrow impact the composition and function of blood? We've seen that bone is this living, changing tissue, and that the blood that sustains our entire body is manufactured deep within it. These two systems are profoundly interconnected. A problem in the factory, the bone marrow, can cause massive issues with everything from oxygen transport to our immune defense, which just highlights how dynamic and completely codependent these systems truly are.